of gas flows.
There you go. Okay, thank you very much. Is this working? Yeah, so it's a great pleasure to be here, a great pleasure to be back. Great pleasure to be here and great pleasure to be back in Santa Cruz. I would like to give you a broad overview of gas flows with MUSE. And in my conclusions, it's late in the afternoon, I'm about to fall asleep because it's 2 a.m. for me, so my conclusions are that IFUs are great to study gas flows. So you just have to remember that. And whenever I say MUSE, you can hear KCWI because essentially they're very comparable. I would like to acknowledge my collaborators, of course, as the MUSE team, which is a very large team, much larger than the people here from many institutions. And the people who have been working with me on outflows and inflows are Ilan, a PhD student who just finished his thesis, Haley, and Johannes. So in the background, you have sort of an artist representation of what gas flows might be around a galaxy when you have 3 streams kind of fueling the star formation in this object with a background quasar here just passing through one of these streams. But there's maybe a more West Coast representation of this CGM would be this picture made by Jessica work in this review that just appear or will appear shortly, where she shows that very nicely in this very pleasing cartoon, the interaction between outflows and accreting gas material. Of course, this picture is not just a fantasy or an artist creation. It's motivated by both observations and results from simulations. In particular, I would like to point out the work by Kyle Stewart that showed a few years ago already that there's a large amount of gas, cold gas, that is orbiting the central object at large distances from the central star-forming galaxy. Here you see the scale here is 25 kpc, so this thing has a diameter that's very large compared to the real radius. A lot of work has been done recently, have sort of confirmed this picture. In the local universe, this cartoon is also motivated by observations, which I think we often forget, is that galaxies have a large amount of H1 that extends sometimes 30 kiloparsecs or more around L-star galaxies, and this is a very common phenomenon. And they end at some radius, but this is the H1 21 centimeters. We know there probably are also lots of gas outside this radius in ionized form. Just something to keep in mind. Of course, the holy grail for studying gas flows in galaxies and the CGM in particular is to be able to constrain and to understand why there is such a low amount of baryons in low mass galaxies. And in particular, we want to put the traditional explanation for this low baryon fraction, is that there are a large amount of material being ejected with large loading factors. But there's really no consensus in these loading factor, in this parameter, both in the observations and in simulations. So here you have different scalings from different simulations. I have very different slopes, different normalizations. Some of this is probably due to definition, but some of it is really intrinsic, and I think we need probably to work on this to have a better uniform view on this. All right, so here are just the outline of my talk. Essentially, I'm going to give you 3 reasons why IFUs are great to study gas flows, because they will serve as illustration for different results that have come out from those studies, both on small scales, on medium scales, intermediate scales, and on large scales. So on the small scales, of course, IFUs are great because you can study the kinematics and potentially you can potentially map also the outflows and emission if you could. On the intermediate scales, the IFUs are great because they serve you as a very powerful tool to identify the host when you have a quasar absorption line. And that therefore provides a key information is the distance between the galaxy and the quasar line of sight, which is the radial information, where you can therefore turn that information into a strong constraint on the mass outflow rate, which you can't do with non-biral observations because the only thing you have is the blue shift from the absorption line, and with just a blue shift and you're missing the location and the information of the location of the gas. On large scales for the CGM, well, we would like to map this also in emission potentially. And just to on one slide show you why I think MUSE is great, because it's a very sensitive spectrograph, or IFU, and this is just a diagram showing the star formation rate sensitivity as a function of redshift. And see here the sensitivity for H beta in the 10-hour observations is around here, 10 to minus 2 in star formation rates, and that corresponds to also the star formation rate for O2 slightly higher, because in 2-hour integrations it's not factor 5 higher, because the O2 of course is brighter than H beta. And with these sort of data sets in the HDFS or the UDF, that's going to be released pretty soon. We can put constraints on the main sequence. This is the first main sequence, or one of the first main sequence at very low masses down to 10 to minus 7, where we can constrain the slope to be 0.8 with this very nice likelihood analysis done by Leonard Boga. Okay, so that was just to show you the potential and the power of MUSE. Now let's go back to outflows. And I gave you the first resonance on small scales. IFUs are great because you can potentially map outflows in emission. And this has been attempted a few years ago at high redshifts by Reinhard Genzel and his collaborators, where they stacked 20 galaxies or 25 galaxies of redshift 2 to see that there's a broad H-alpha component that is more extended than the star forming component. But of course, as a stack, it's very difficult to get information out of this stack or to map in 2-dimensional. And here I would like to introduce you to this galaxy HDFS number 13 in this HDFS observations that appear this year on the archive. You see the morphology here from the HST. This galaxy is fairly compact, high flat radius of 2.5. And if you look at the spectra, it has, of course, some traditional absorption lines where you can study winds and absorption. If you would zoom, you'd see the clearly blue-shifted component in these absorption lines from magnesium and iron. But you also have these non-resonant iron-2 emission lines here, which extend much larger than the stellar continuum or the O2 star-forming regions. So here the dotted line shows the kinematic major axis. So the galaxy is blue-shifted here and red-shifted here. Has a low inclination, about 30 degrees, has high star formation rate. But the iron-2 non-resonant emission has a morphology that's very different and is more extended, has a high flat radius of 4 kiloparsec. And so now we can try to see if you can map this emission by subtracting galaxy model. This is what we have done here. So here again, you see this now the observed iron-2 emission from these 4 non-resonant emission lines. And if you do a long slit, pseudo-long slit along this direction here, you have this PV diagram. This is the position along the slit and then velocity. And the green contours show the star formation emission. And you can see here, you should supposed to see in this diagram, there's a C shape here with 2 fingers extending in this direction, corresponding to blue shifted emission. And you also have a little bit of a finger here on the red side when you have also a little bit of redshift emission. And this, we can then constrain the morphology of this emission from the winds by subtracting the motion from the ISM. And this is what we get. This is sort of the first 2D map of an emission of a wind at high redshifts, redshift 1 or so. When you can see this emission here for the blue component and a little bit from the red component. And our interpretation is that we have this blue component that's pointing towards us, whereas the red component is on the back side, of course. Interestingly enough, I'm going to I'll go very quickly over this, is that of course, galaxies can also have magnesium 2 in emission. This is people here, like X, have worked on this, and I've shown that even though it's a resonant emission, you can also have emission in this trough. But the iron-2 emitters, which are blue, and the magnesium, that are in red, and the magnesium 2 emitters lie in very different location in this star formation mass plane. Here you can see here that the low mass are more, that's where you find more magnesium 2 emitters, and the high mass is where you find more iron-2 emitters. We can discuss this more later if you're interested as why that would be the case. And let's move to my second reason why it's great to study outflows with IFU is that when you have a wide field of view like MUSE or KCWR, you can potentially try to map the CGM in emission when you put a bright source here in the middle. For instance, you might want to put a quasar in the middle that might shine on the CGM, and you can see the reprocessed light of the quasar back towards you. And this is what has been done at Redshift 3 by the team of Simon Liddy and Sebastiano Cantalupo. It was published last year when they studied this, the emission in Lyman alpha around radio-quiet quasar. They had a sample of 18 radio-quiet quasars, and they found this gigantic nebula of Lyman alpha after subtracting the emission from the quasar, of course, and in 18 of the cases. And look at the scale here. This is 100 kpc, and so these structures extend to very large distances from the central object. Sometimes 100 kpc in diameter, sometimes 300 kpc in diameter, and sometimes if you go deeper, you end up finding that it's filling the entire Muse field of view, 1 arc minute. That corresponds to almost 400 kpc. But it's very difficult to turn this information and this beautiful data into a constraint on the CGM mass. So you would like to know how much mass is in the CGM that you see here in emission. It's very difficult because you don't really know the gas temperature, the gas density profile. You have to rely essentially on very complex relative transfer modeling. There has been a number of papers here a few years ago, and of course KCWR is starting to show similar things as the paper by Chris Martin on the Paloma version of it. So the third reason why it's important to study gas flows with IFU is that, as I said earlier, is that they provide you this key radial information. So when you have a background quasar and you have this line of sight producing absorption line, when you have galaxies in the vicinity of this line of sight, the IFU allows you to identify the host immediately after, and also therefore the impact parameter, so the distance between the galaxy and the sight line. So I like to work with the magnesium line. Some people prefer other lines, but I like to work with the magnesium 2 line because it's a doublet, so it's easily identifiable. You can create. You have large samples of quasar absorption lines with magnesium 2 absorption from the Sloan survey, of course. But you can see here these two examples, that were supposed to be in different orientations. Like the line of sight might cross the other part of the disk, or might cross also the an outflow. That depends on the geometry. So it's critical to have the information on the geometry or the inclination of the galaxy with respect to the line of sight when you do these studies. And that's not possible with the IFU. So the IFU really provides you with a wealth of information that you can then turn around in physical constraints. So geometry matters. And so this is a slide to introduce to you the Muse gas flow and wind survey. So this is an absorption selected survey where we start with the quasar catalog with strong magnesium 2 absorbers of around 0.8 angstroms or higher. And we select particular sight lines which have multiple 3, 4, 5 magnesium 2 absorbers per line of sight or per field. And that gives us a large sample in 20 fields of 85 absorbers. And therefore that will lead to 85 potentially quasar galaxy pairs. This redshift range from 0.4 to 1.5, because that corresponds to the wavelength range where you can study the galaxy in emission with O2. Sorry for the mix-up here for the conversion between PowerPoint and LibreOffice. But so we also, for each of these quasars, have high-resolution spectra, and the survey has just been completed. And so now we can begin to look at the statistical results from this analysis. So here's just a cartoon representation here of a sight line with multiple magnesium 2 absorbers. And the redshift distribution is from, as I said, from 0.5 to 1.5, but mostly around redshift 1. So we have a catalog of absorbers. We don't know where the galaxy is. So we just have to use an IFU, point Muse at the field, and then, because we know the redshift of this absorption, select the right slice in the IFU to identify the galaxy in the field of view. So here's one of these Muse observations, and we had just select with 3 absorbers at 3 different redshifts, and we have to then look at each slice to find the galaxy responsible. And for the radius of 100 kpc would be correspond to this sort of size. We have a success rate in doing so in detecting the host galaxy in about 75% of the cases. And we have, as I said, a lot of information. We have with this IFU observation star formation rates, of course, from the O2 lines, the kinematics, the rotation curve, the inclination, and the distance to the line of sight. So one question that comes often is like, well, okay, you see a galaxy close to the line of sight, like in this case or in that case, but are there more? And before we had only symphony, and we had a very small field of view, like in this case. And you can see here with thanks to Muse, we can see in this narrowband image that there are really no galaxies around with this sort of star formation limit. There's one here that's very far, it's like 250 kpc or so. So it's not really related to the CGM that you're probing the line of sight. Here's another example. The impact parameter is slightly larger, but there's really no other companions down to this very low limit. But we can look at the statistics. How frequently is this? It's just a lucky case or a few cases. So now we are just beginning to look at the statistics. And here he has the histogram of the number of galaxies per field in blue and the number of galaxies within 100 kpc in red. And you can see it's like most of the time we have 0, 1 galaxy within 100 kpc. So there's really no ambiguity to the identification of the galaxy with corresponding to the absorption line. So this picture here that you go find is that there's a group like the MET1, MET2 group. Is really not a common situation. And so when you study galaxies with galaxy outflows with quasar absorption lines, this situation is really not frequent. So you don't have to worry about it too much. It does happen. There's a tail here when we have 3 or more within 100 kpc, but it's very rare. There's also a few passive galaxies which have been uniquely identified within 100 kpc. So we can now also look at the azimuthal distribution. So this is the angle between the location of the quasar to the galaxy major axis, where 0 degrees is on the major axis and 90 degrees is on the minor axis. And here is the distribution. And from that, we can select galaxies that are galaxy quasar pairs, where the quasar is most likely to probe the winds or most likely probing the extended gaseous parts of the disk. So by selecting quasar galaxy pair where the quasar is aligned with the minor axis, we can study the radial dependence as a function of impact parameter. And you can see here this very nice correlation between the coronal width that corresponds to the column density of the gas as a function of impact parameter. And I think that's a very strong constraint of models because it's very flat. And I would like to see more models trying to reproduce these observations because whether you're probing the gas along the minor axis, so outflows or along the major axis, you have different radial dependencies. So the CGM is very anisotropic around galaxies. And we can look all at the outflow properties. Also, now since we have all of this information, we can compute the loading factor, so the outflow rate as a function of galaxy mass. And this is what we find now with the sample, that's largest sample that we could do this with constraint from quasar absorption lines, and we find loading factor of unity also. What's interesting is that the outflow speed compared to the escape velocity is typically lower than the escape velocity. So for high mass galaxies, most of the time the wind that we probe with these tracers, low ionization lines, do not escape or would not escape, except maybe in some few low mass cases. So that remains to be seen as whether there's a clear transition or if there's just small number statistics. But that's where we are right now, so stay tuned. We can also look at the properties of galaxies when the quasar is aligned with the major axis. So now we can study the kind of the extended parts of the disks of galaxies with impact parameter of 30 or 40 kpc or 50 kpc by comparing the rotation curve we get from the kinematics to the absorption line that we get from the quasar line of sight. And you see in this case, there's a strong component that's highly aligned in velocity with the galaxy rotation curve. So we begin to probe the extended parts of disks at large distance from the star-forming galaxies. And of course, you might have seen work by Kristen Martin and her student that shows very similar results. So the rotation seems to be, or the gas is seen in absorption with quasars. Here it's L-ray, so it's low resolution, so the R bar is larger, but still it's on the same side, so in the same side as the rotation curves. And this would put strong constraint on gas inflows in particular. I would like to end by a note of caution, is that all survey is absorption line selected survey, whereas most other surveys for galaxy quasar pairs are galaxy selected surveys. So they start with a sample of galaxies, and then they looked at the quasar that is the nearest quasar within 150 kpc or so. The Costello, Burst, and the program by Kristen Martin. But these are flux limited or stellar mass limited surveys at a very high mass, about 10 to the 10, or slightly lower, maybe than 10 to the 10. And so therefore you don't really know whether there are smaller galaxies within 150 kpc that you would not see. So that's why it's important to have a very low star formation rate thresholds where you can detect all the galaxies up down to 10 to the 8 within your impact parameter. And which led me to just put my conclusions. So I've shown you that winds and emission with iron 2 non-resonant emission extends 4-5 kpc. These two type of emission are disjoint. And then the CGM can be probed in emission around bright quasars only currently. Maybe in the future we can do that around normal galaxies. And here is sort of the summary of the gas flow properties that are extend about to 80, 100 kpc. It's very high anisotropic. This selection on magnesium 2 traces really individual star-forming galaxies. Outflows do not escape. The loading factor is around unity. And we begin to probe the gas kinematics of accretion. Thank you very much.
Okay, questions? What was the evidence that the gas is actually outflowing the outflow rates and wind speed? But what was the IQ data signature?
So there are two things. So first is we can look first at what are the sight lines that are most likely to probe outflow. So we select pairs that have high alpha, so they are along the minor axis. And then we looked at the kinematics. And the kinematics I didn't have the time to show, but they have asymmetries in them, depending on the orientation of the galaxy. And this asymmetries is understood with a simple biconical model where you just change the inclination. And this asymmetry that we see in the data is what you expect with this simple biconical model.
Any other questions? Okay, great. Thanks again.